Assalamualaikum and hi. My name is Muhammad Mahmeh. Match number M8171. I'm gonna do the chapter 1 about the heat convection. Introduction. Heat convection is a process of heat transmission in which heat is transferred through the mass motion of a fluid such as air. When the surrounding fluid of an item is heated, heat convection occurs and energy is transported away from the source of heat. When the surface temperature of fluid differs from that of the surrounding fluid, convection heat transfer occurs. The governing equation of heat convection behavior is the Newton law, which is QH equal to HA bracket Ts over minus Tf, where is QH is convection heat of surface, A is cross-section of boundary surface, Ts is the surface of temperature, and Tf is the temperature of the surrounding fluid. The objective for this experiment is, first, to investigate the transfer of heat by convection both naturally and by force. Second, to determine the effect of fin addition on the heat transfer characteristic.
Assalamualaikum warahmatullahi wabarakatuh. My name is Wan Muhammad Alif bin Muhammad Rani. Now allow me to continue with the literature review. First, let me share the literature review on heat conduction. Basically, heat conduction, or also known as thermal conduction, is the movement of heat from one object to another one that has different temperature when they are touching to each other. For example, our hands can be warmed by touching the hot water. When the cold hands touch the hot water, we will feel warm and hot, which means the heat flows from the hotter object to the colder one. And people also make things with different thermal conductivity, such as cookware to heat things, insulated containers to keep hot things remains hot, and the cold things remains cold. Other ways to transfer heat are by thermal radiation and or convection. Usually, more than one of these processes happen at the same time. And the conventional symbol for thermal conductivity is K. For the linear conduction of heat transfer by linear conduction can be thought as of heat passing through the plane walls. For example, heat conduction may occur within the house's walls and it would pass through the wall surface in the usual direction. A wall surface that is nearly isothermal can be verified by taking temperature readings at many locations on the inner or outer wall surface. Each wall, including the top, bottom, right, and left walls, is almost sharing the same number of temperatures in this case. Consider a plane wall with a thickness of L and a thermal conductivity of K on average. The temperature of the two surfaces of the wall is held constant at T1 and T2. It has T for one-dimensional steady heat through the wall. Next, for the Fourier's law, which is the law of heat conduction, and this is the common equation used in the law of heat conduction, which is Q equal to Ka times by dt over dx, where Q is heat flow rate, K is the thermal conductivity of the material, A is the cross-sectional area of the conduction, and dt is the changes of temperature between 2 points, and dx is the changes of displacement between 2 points. And this graph or figure shows the linear distribution of heat conduction with different materials. Due to the various materials, the number of constant, which is K, varies, while X is the length of each material and T is the temperature. The rate of heat conduction through a wall is proportional to average thermal conductivity, wall area, and temperature difference, but inversely proportional to wall thickness as shown in the graph. That's all from me. Thank you.
Good morning to everyone. My name is Stanley Sirin and my metric ID is MA1844. So today I will be presenting for the experimental setup. For the equipment that is used in this experiment, we will be using the model HE105 Soltec Heat Conduction Study Bench Unit. The following are the labels of components in the equipment, such as number 1, the control panel, number 2 is the heat power indicator, and number 3 is the heat power regulator, and so on. As for the materials that is used in this experiment, it is for the linear module, we will be using the brass and the stainless steel with the following measurement. As for the radial module experiment, we will be using only brass with the following measurement. As for the procedure for the first experiment, which is the linear module, first we need to make sure that the main switch is off. Then we will insert the brass specimen into the linear module and clamp it together. Water supply is then turned on and it must flow from free end of the water pipe to the drain. Next, the heater power control knob control panel was turned to fully anti-clockwise position and the sensor leads were connected. And then turn on the power supply switch and the main switch and load the NIDEC, MX and DesiLab software. And then we will set the heater power control to 20 watts and wait until it reaches steady state condition before recording the result. Repeat the step for other value between 0 to 20 watts and then repeat step 1 until 6 using the stainless steel and record the result. For the experiment 2, radial module, the first step and until the third step is the same as in the experiment 1. However, in the fourth step, 6 sensor leads is connected to the plugs on top of the radial module. And then turn on the power supply switch and the main switch and load the software and set the heater power control to 20 watts and wait until it reaches steady state before recording the result. Repeat the step for the other value between 0 to 20 watts. That's all from me, and I will pass my presentation to other group member. Thank you.
Assalamu alaikum. I hope everyone is doing well. My name is Ali bin Hammam, and my part is going to be the results and calculations. So without further ado, let's get straight into it. There are 3 sub-points in the selection: experiment data sheet, relationship between temperature and distance, relationship between temperature and 1x. Before we continue the first sub-point, as we know, all laboratory sections are held through online platforms, so all selected data are provided by lecturer. Back to the experiment data sheet. We are only given linear model, so we just explain what the data is provided. As we can see, there are 4 input power for the linear model, which are 5 watt of stainless steel, 5 watt of brass, 10 watt of stainless steel, and 15 watt of stainless steel. Beside that, the variable for this experiment are the distance x and 1x. What we observe of this experiment is the temperature of the input power, so we listed out the average temperature for every measured distance. For better understanding about the relationship between temperature and distance, let's have a look at this graph perspective. So as it's shown in the graph, there is nearly linear graph on the temperature distributions compared to the theoretical graph given a negative slope or temperature gradient, which cause inverse relationship between measured temperature and distance. Therefore, the further the distance from the heater, the lower the temperature. Heat is conducted in the direction of the present temperature. As we can see in this graph, the lowest temperature is the 5 watts of brass compared to the 5 watts of stainless steel. The reason why is that the brass has higher thermal conductivity than that of the stainless steel, which affected the temperature distribution through that element. Lastly is the relationship between temperature and ln x. So in this figure, we can see that the ln x increases the temperature value. The thermal inhabit, due to the heat for the offiation, have no longer enough energy to constantly heat up the material per meter for 1 degree to conduct a cell. That was my part. I hope it was clear and obvious. Now I'll let you continue with my partners. Thank you so much.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syahban Mazet, metric number MA156, and I will be continue for the discussion for the heat conduction lab. So Using Fourier laws of thermal conductivity, we can estimate that the temperature gradient between two separate systems. Also, in this experiment, when we use three different power levels, which is 5, 10 and 50 watt, we will find or we will calculate the thermal conductivity. So basically, we will use two different materials, which is the stainless steel and the brass. So from this table, we can see that the thermal conductivity of brass with 5 watt is higher than that of stainless steel with 5 watt, and stainless steel with 15 watts produce a higher value of thermal conductivity than stainless steel with 10 watts for the same type of specimen but different power levels. So the condition that we can say is the higher the thermal conductivity rating, the closer the material is to be conducted, and the lower the value of the thermal conductivity, the more likely it will be an insulator. Next, for the phenomena error that maybe exists in this experiment or lab, which is one, the environment, second, the material qualities, and lastly, the length of the heat channel. And there are also a few systematic and random flaws that will detract from the rating outcomes, and this will affect the outcome of this experiment. I think that's all from me. Thank you.
Hi, my name is Muhammad Arif Shaimi bin Saidi with metric ID MA18153. Today I will present chapter 5 for this lab experiment. In conclusion, conduction is the transfer energy from the more energetic particles of a substance to the less energetic particles nearby. Due to heat conduction from the room through the aluminum can, a cold can drink in a warm room heats up to room temperature. The geometry, thickness, and the material of a medium all affect the rate of heat conduction through it. The thermal conductivity of a material is heavily influenced by several factors. Increased thermal conductivity in phase transition materials enables a higher heat transfer rate. This can reduce the amount of time it takes for phase change materials to discharge entirely. Thermal conductivity is a property of a substance that may be determined using experimental data. This experiment involved temperatures range from T1 to T7. The thermal conductivity of brass is greater than stainless steel. Brass has a higher thermal conductivity than stainless steel. The lower the value, the more similar the material is to an insulator. Errors in phenomena are possible, but they are not necessarily correct. This experiment may be used by students to confirm the material's thermal conductivity and investigate Fourier's law for the linear conduction of homogeneous heat. That's all from us. Thank you.